We've been talking about the three-dimensional shapes of molecules. One other thing to note is how to draw three-dimensional molecules in 2 dimensions. By convention, we put the central atom in the plane of the paper. Then, however many other atoms you can fit in that single plane, you should connect with a straight line. Then anything that's going in front of the plane, use a solid wedge. Anything behind the plane, you can use a hashed wedge. So let's look at an example of what it looks like. So you see here, the first 3 are all in one plane, but when you get to tetrahedral, you put your central atom in the plane of the paper. 2 other atoms can go in that same plane. Then for the one coming towards you, you can use this filled in wedge. And for the one going behind, use some dashes. And then you can see some of the other examples for the other types that go in more than one plane. We've talked about geometry around simple molecules that only have one central atom, but many molecules of interest are going to have larger structures that have more than one interior atom. What we do there is we describe the shape around each central atom in the sequence. So if you look at this molecule here, this carbon has 3 hydrogens and another carbon, so 4 groups, and they're all atoms. So it's tetrahedral. The center carbon here has 3 bonds and no lone pairs, so it's trigonal planar. Our oxygen here has 2 bonds and then 2 lone pairs. When you see structures like this, you might have to fill in the lone pairs in your head just because they're not there. Make sure you're thinking it through because we don't always draw in lone pairs. So our oxygen here is tetrahedral bent. So let's practice. Predict the molecular geometries in H3BO3, that's boric acid. Our boron there is our central atom, connected to 3 oxygens, and each oxygen has a hydrogen attached to it. Remember, boron is one of our exceptions in Lewis structures, where it is content with 6 electrons around it rather than the typical octet. So for our boron, we have 3 groups, no lone pairs, and so our molecular geometry is going to be trigonal planar. All of our oxygens are equal to each other. They all have 4 groups, 2 lone pairs, and 2 bonds to other atoms, which makes them tetrahedral bent. So there's our shape. You can see here it's drawn nicely with the predicted bond angles as well. Couple more practice for you. What is the approximate angle of the indicated oxygen-carbon-oxygen bond in the citric acid molecule below? So our carbon here has 3 groups, no lone pairs, which means our predicted bond, our shape is going to be trigonal planar. And that also means that our bond angle, you would start with 120 degrees. Because there are no lone pairs present, nothing should push it drastically out of shape. So the answer is A, 120 degrees. One more multiple choice question for you. Determine the electron geometry of the labeled oxygen in aspartic acid. So our oxygen there, you would have to recognize that it has 2 lone pairs on it. which means that it is tetrahedral bent. And in this case, just bent is going to be the answer. We don't always put the tetrahedral or trigonal planar bent in front, so just a bent structure.